Yesterday or in the previous class, we have been discussing Lenz's law. Lenz's law, first law and second law. And in the Faraday's laws of electromagnetic induction, second law gives the magnitude of induced EMF as E equal to is given by the equation induced EMF E equal to phi2 minus phi1 divided by T2 minus T1, or that's equal to phi2 minus phi1 divided by delta T. Suppose we have a coil, as we have discussed earlier. We have the coil. Let us imagine a coil, and at we are taking two instants of time, that is t1 at t1 second and t2 second. At t1 second, let phi1 be the flux associated or flux linking the coil, and let at t2 second let phi2 be the flux linking the coil, that is having n number of turns, capital N number of turns, and T1 is less than T2, that is first T1 comes, then T2. For example, T1 is 3 second, T2 is 10 second, or something like that. Okay, T1 means third second and T2 10th second. So two time instants we are taking, and the flux linkage associated with the coil is phi1 and phi2 respectively. Then according to Faraday's second law, what will be the magnitude of EMF, induced EMF? E will be equal to phi2 minus phi1 divided by T2 minus T1. Since the coil is having n number of turns, so this is multiplied by capital N, and this is equal to, that is E is equal to, I'm applying the limit, that is actually E is equal to N delta phi, that is delta phi means phi2 minus phi1, that is change in flux associated with the coil, delta phi divided by delta T, and I'm applying the limit. E is equal to limit delta T tends to 0, that is I'm making this delta T very small, that is infinitesimally small. That means the limit delta T tends to 0, delta phi n delta phi actually divided by delta T. So this is nothing but your E is equal to n you can since it is a constant, you can take it out. So n limit delta T tends to 0, delta phi by delta T you will get, that is nothing but your differentiation, d phi by dt. This is the magnitude of the induced EMF, right? Now I have to find out, actually Michael Faraday conducted this experiment, okay, in 19th century, okay, and later a scientist known as Lenz given not only the magnitude but also its polarity of the induced EMF, or the direction of the induced EMF, you can say direction. So polarity or direction of the induced EMF is given by another law which is known as Lenz's law. And Lenz's law, the direction of the induced current, or the polarity of the induced EMF. The polarity of the induced EMF is nothing but induced EMF cause a current to flow if a closed path is observed. Then the polarity of the induced EMF means the direction of the current through that path, through the closed path. So the direction of the induced current is such that it opposes. That means we have an induced EMF. We have an induced EMF E. Okay, E we have, and this EMF will cause a current known as induced current. In the circuit or in the closed path. That is, if the path is closed, a current will flow, like our galvanometer deflection. Okay, due to this induced current, the galvanometer deflects. So, the direction of this current is given by Lenz's law, and Lenz's law states that the direction of the induced current is such that it opposes the very cause. So this is important. The very cause which produced the induced current. Through magnetic action. That means, let me again recall our discussion of that experiment done by Michael Faraday. We have a coil like this, and we have this is connected like this through a galvanometer. I'm not showing that galvanometer here, and this north and south pole bar magnet. North pole, south pole bar magnet is moving like this, so that the flux linkages will change as it moves from right to left. Okay, so that according to Faraday's law of electromagnetic induction, that is second law. First law. We will have an induced EMF established in the circuit, and that in the induced EMF will cause a current to flow, current I to flow, right, like this. So the direction, the Lenz law is what is stating that the direction of this induced current is such that it opposes the very cause which produced the induced current. That means the cause here is the movement of this bar magnet. And the movement of this bar magnet will result in a flux linkage, change in flux linkage, right? So the motion of this bar magnet from right to left, like in this manner, that is the cause of this induced current. So the direction of this induced current is in such a way that it should oppose this change in magnetic flux linkages. So, or in turn the motion of this bar magnet in the right to left manner. So what has to be observed is that here we have two poles, north pole and south pole. In order to oppose the motion of this bar magnet from right to left, okay, right to left, that means you should have a force from uh, left to right in this direction, right? In order to have a force, this current carrying conductor should act as a magnet such that it should have a polarity, or it should have north pole and south pole in such a manner as to oppose the motion of this bar magnet, the external bar magnet. Okay, so in order to do that, the north pole, here a north pole should come, and here a south pole should come. So that north pole will repel, so that a force in the in from left to right is established, so that it opposes the motion of this external bar magnet, right? So in order to have this kind of polarity for this magnet, this in order to induce north and south pole here, what has to be the current flow direction should be like this, yes, in anti-clockwise direction. That means if you observe this coil in this, by viewing in this direction, or in this direction, on this side, then the coil will appear like a circular, yes, circular in a circular manner. So the current flow direction must be such that it should get a north pole here. That means north pole here means, yes, the current flow direction must be in this manner. That means in anti-clockwise direction. Anti-clockwise direction. Okay. Yes. So anti-clockwise direction means current should be like should flow like this, in this manner, and enters into the coil, and yes, in this anti-clockwise direction, like this, like this, like this, like this, like this, and leaves the coil like this, right? This should be the current direction. So with this direction of current, the polarity of induced EMF must be positive here and negative here, right? So that current is always flowing from higher potential to lower potential in this way. Okay, this is what the Lenz said in his law. That is, the direction or the polarity of the induced EMF is given by Lenz's law. Okay, which states that the direction of the induced current is such that it always opposes through its magnetic action the very cause which produced the induced current. Okay. Yes. Now suppose we are moving this bar magnet from left to right like this. Then the induced current should flow in such a way that it should oppose the cause. That is, it should, that is, the bar magnet is moving away from the coil, so it should act in such a way that it should bring closer to the coil, so that the with this polarity, north and south pole of bar magnet, here the induced polarity of the magnetic field must be south and north in this manner, so that south and north pole will attract, so a force is experienced like this, right? So in that case, here the coil, which looks like a circle when you look from this view. Okay, here from this view it looks like a circle, so that its direction, current flow direction, must be opposite to that in the previous case, in the clockwise direction. Okay, clockwise direction like this. So that current in the circuit will be having a direction like this. Okay, yes, like this, clockwise, this like this. So that the polarity got changed like this, plus here and minus here. Okay, so that is what also the Michael Faraday observed, because the bar magnet, when moved in the opposite direction, the galvanometer is deflected in opposite direction. Why? Because the direction of flow got reversed, and the direction of flow is given by Lenz's law. Later Lenz discovered the direction. So, and the mathematical modeling or the mathematical representation of Lenz's law, or the whole Lenz's law plus Faraday's laws of electromagnetic induction, can be written as E is equal to minus n d phi by dt, and this negative sign is our Lenz's law, and this is our Faraday's law, Faraday's laws. That includes Faraday's law 1 and 2. Now we have also discussed the methods of producing induced EMF in the previous class. There are three requirements to producing, for the production of an induced EMF in a conductor. Namely, first, the presence of a conductor. Secondly, presence of a magnetic field B, and finally the linking or cutting of the magnetic flux lines by the conductor, or you can say relative motion between the magnetic field and the coil. Okay, and by using now we are going to discuss the methods of producing induced EMF. And the first method is by using a stationary conductor, a stationary electromagnet and varying the magnetic flux by supplying AC current to the electromagnet. That means we have, yes, in our previous discussion we have, yes, we have a circuit like this, and we have a circuit like this, positive, okay, positive negative battery and a switch we have, okay, and we have, so by operating this switch, by closing and opening this switch, that is by operating this switch, we have current induced in the nearby coil, right, nearby coil. So this is what you call as statically induced EMF, where the magnetic flux produced by this flow of current in the first coil is made to vary with respect to time. Here the flux is varying, flux is varied, means yes, flux is phi is varied with respect to time, and the coil is stationary. The two coils are made stationary. Or this can be done in another way also, by replacing this battery source by an AC source, so that alternating current waveform you have studied in your plus 2 classes, that is, it is alternating in nature. That is, after every half cycle its polarity got changed, positive negative, its polarity got changed, so that the current flow is also got changed, current flow direction is also got changed, and also it is also varying with respect to time, so that the phi, flux phi is also varying with respect to time. Phi of t is a function of time, so that the flux linkage, that is n phi, flux linkage associated with the second coil is also got varied. So the condition for the induced EMF is satisfied, right? So an induced EMF is produced in the second coil. So this method is known as statically induced EMF, or this type of induced EMF is known as statically induced EMF, where the conductor, the conductor is stationary, is at rest, that is static, and the flux linkage associated with the conductor is changing with respect to time. That is what the definition of statically induced EMF. Now also we have discussed the other methods, that is by the motion of the conductor. That is, you have studied in your plus 2 classes, that is motional EMF. So this motional EMF is also known as dynamically induced EMF. Dynamics means something which is moving. So dynamically induced EMF. Okay, that is also you have studied. Then and we have the, yes, how to produce the dynamically induced EMF. In order to have the dynamically induced EMF in a coil, we have several methods to produce it. Okay, so the methods are by changing the magnetic field B. First method, by changing the magnetic field B is changed. Then second method is by changing the area, effective area of the coil. Suppose that means suppose let us consider a coil, a single turn coil like this, and it produces an area A inside this coil, right? And let it be area A. And this area A is a vector quantity, and that means it has both magnitude. Magnitude is given by pi r square, and its direction. It has also got direction. The direction of this area vector A is given by the normal to this plane. Normal to this plane containing the coil. Okay, that is the direction of this area. Now, suppose we have this singleton coil is placed in a external magnetic field B, vector B, like this, and its direction is exactly parallel to this, parallel to the area vector A, okay, like this. So this is our magnetic field, and yes, this is position A, position 1 of this singleton coil. Now what I am going to do is I am just tilting this singleton coil like this, tilting this singleton coil, yes, like this, I am tilting this singleton coil. Then what happens is the direction of area vector has changed. This again, this is our magnetic field direction of the magnetic field. Now the area vector direction will be again normal to this plane, that is, it is having some angle like this. Yes, so the area vector, magnitude of this area vector A magnitude will be the same as before. But the direction, what happened to the direction? Direction, we have the direction of this area vector exactly normal to this area plane, or the plane containing the area. So the plane got changed, plane got tilted by an angle theta from the horizontal axis, like this, theta. So what happens to the normal vector direction? Previously it was parallel to this magnetic field direction, but it is also has got changed by an angle theta direction. Okay, this is vector A, and now let us calculate the flux associated. Let phi be the flux linking the single turn coil. That is, the flux linkage psi is equal to n phi, and that will be equal to, here n equal to 1, so psi will be equal to phi. So if you calculate phi, we have phi formula, the magnetic flux equal to B, the magnetic flux density into area, B into area. Actually this VA is defined where, for this case, position 1 only. But in general, phi is defined as the scalar quantity phi is equal to vector b dot vector a. That means equal to ba cos theta, ba cos theta. Right. So the effective area in when coming to this position 2 of the singleton coil has reduced by a factor cos theta. So the new phi, let me notate it as phi dash. Phi dash will be equal to b into a into cos theta. So earlier it was phi, and phi e is changed from phi to flux linkage is changed from phi to phi dash. That means we have satisfied the condition for the induced EMF, right? That means a flux linkage, change in flux linkages is observed with respect to time. So definitely the coil, in that coil, an induced EMF E will be produced. And also, if the coil is closed, that means it offers a closed. If it is offers a closed path for the flow of current, then a current will flow such that the direction of that current is given by the Lenz's law. Okay. This is a method to produce dynamically induced EMF. Okay. Now we have another method of producing the dynamically induced EMF. Yeah, by by changing B. B means the magnetic field intensity. Okay, and yes, this, and also the third, yes, this third method is by changing the angle theta induced EMF by varying by changing the angle theta, which is previously we have discussed, right? Theta. So in all these cases, we can produce dynamically induced EMF. Okay, then our next topic is Fleming's right hand Fleming's right hand rule. You have studied the motional EMF, okay, and the motional EMF, for the motional EMF we have a an important rule associated with the motional EMF or dynamically induced EMF, that is known as Fleming's right hand rule. Okay, now consider a method that produces the dynamically induced EMF in which the conductor is moved in a uniform magnetic field. Yes, like this. Yes, this is our uniform magnetic field in a uniform magnetic field that is north and south pole. We have field lines from north to south pole in the direction shown as shown in the figure. And also we have a conductor like this, and the motion of the conductor is allowed to move, is free to move in the upward direction in the uniform magnetic field. So in that case, the magnetic uh, field associated with the conductor is changing with respect to time due to the motion of this conductor. So what happens is, according to Faraday's law, any induced EMF is happened in the conductor. So the direction of that induced EMF or induced current, it will be in such a manner given by the Fleming's right hand. That means the Fleming's right hand rule states that stretch the first finger, the central finger, and the thumb of your right hand in mutually perpendicular directions. Mutually perpendicular direction. That means all these uh, fingers are directed in mutually perpendicular manner. Okay, like a three-dimensional system. Three-dimensional your x, y, and z axis. Three-dimensional axis. You have to project your first finger, then your central finger and thumb of your right hand. Right hand. So right hand, that is important. And then you are adjust your wrist so that the first finger points in the direction of magnetic field. Okay, magnetic field that is emerging from north to south pole, like as shown in this here, as shown in this figure 512. It is shown, okay, like this. That is the forefinger, the first finger, that is along the direction of the magnetic field lines, and the thumb indicates the direction of motion of the conductor. Then the center finger or middle finger indicates the direction of the induced current. That is Fleming's right hand rule. Okay, yes. Now we will solve a problem based on our discussion so that we will get more clarity in the concepts. The example problem is like this: a conducting circular loop, a conducting circular loop, is placed in a uniform magnetic field P, is placed in a uniform magnetic field B, and magnitude of B, magnetic flux density, is given as it is equal to 0.02 Tesla. That means at any if you take any point in that uniform magnetic field, then the magnitude of this magnetic flux density will be 0.02 Tesla everywhere. That is what I mean by uniform. Uniform. The uniform means equal. Okay, B equal to 0.02 Tesla with its plane perpendicular to the field. With its plane means plane containing this conducting circular loop with its plane. He said that it is perpendicular to the field. He is perpendicular to the field. So it looks like this. That is a circular loop, connecting circular loop like this, and its plane is perpendicular to the direction of magnetic field. Sorry. So sorry. Just like this, perpendicular. This is B, and if you take P, any point P in this magnetic field, and it is having 0.02 Tesla. That is what I mean by uniform magnetic field, perpendicular to the field. Okay, yeah, yes, and somehow the radius of the radius of the radius of the loop starts shrinking at a constant rate of at a constant rate of 1 millimeter per second. That means we have the radius r of the circular loop r, and the examiner said that this r radius r is somehow shrinking at a constant rate of 1 millimeter per second. That means this r is reducing. That means for after 1 second after 1 second of time, this r will be reduced by 1 millimeter, so that the new coil circular loop will be somewhat smaller in size. Okay, so that means this area, the the magnitude of this area vector A is got reduced. Okay, here it is r dash. So that is our problem. So in this problem, the area is the magnitude of area is changing. That means phi which is equal to B A cos theta. Here theta equal to 0 degree, because he said that the plane of circular loop is exactly perpendicular to the magnetic field. So that means the normal area vector will be parallel to the magnetic field. So theta will be 0 degree. So what we will get, phi is equal to BA. But the problem here is the area after 1 second, after each 1 second, it is got reduced. Area is reducing, and at one point of time, this area will become 0. So that means this area is changing, means this phi, that is magnetic flux associated with the circular loop, is also changing. So according to Faraday's law of electromagnetic induction, an induced EMF E will be induced in this circular coil, and it is given by E is equal to minus N d phi by dt, and equal to and the magnitude will be equal to modulus of E equal to n d phi by dt, and that is equal to n, that is number of turns, is here it is 1. So d phi by dt, then d phi by dt means E is equal to d phi by dt is equal to d by dt of p into a, and this p is a uniform magnetic field, so p is a constant that can be taken out, that is b into dA by dt, and this area of a circular loop, circular coil, is given by pi r square, and this radius r is a function of time, and it is it is given that r of t, r is a function of time, and it is shrinking at a constant rate of 1 millimeter per second. That means this radius is changing with respect to time. So what happens is we have E is equal to V into d by dt of pi r square, that is E is equal to P into pi into d by dt of r square, that is E is equal to P into pi into d by dt of r square means 2 into r into dr by dt, because r is a function of time t. So if yes, this is just mathematics. Okay, n into n x d by dt of x power n equal to n x power n minus 1. So n x power n minus 1, 2 into r power 2 minus 1, and into dr by dt function. Yes, then E is equal to, and our he is the asking the induced EMF. That is, in our question he has given that find the, yes, our aim is to find the induced EMF in the loop. Induced EMF, magnitude of induced EMF in the loop at an instant when the radius is 2 centimeter. At an instant the radius is 2 centimeter. Okay, so we got the formula here. So you substitute E is equal to V is given as 0.02 into pi into 2 into, yes, R is given at 2 centimeter of radius. So 2 into 10 power minus 2 into dr by dt. Dr by dt means rate of change of radius with respect to time. So the rate at which the radius is shrinking is given as 1 millimeter per second. So it will be 1 into 10 power minus 3 meter per second. So if you multiply all this, you will get E is equal to E is equal to some 2.5 microvolt. So this magnitude of induced EMF is, that is this circular loop is shrinking. Okay, is shrinking, and at this, for example, at this instant of time we have r dash equal to 2 centimeter. Then the examiner is asking you to find out the induced EMF at this instant of time. So, and we have found it is to be E is equal to 2.5 micro. So that is our example problem. How to solve the example problem. Yes. Now we are going to our next topic, self and mutual inductances. Self inductance and mutual inductance. Self inductance is represented by capital L and mutual inductance denoted by M, capital M. And these two L and M are defined for a coil, for inductors, for coils. Okay. Previously we have discussed that the statically induced EMF. So let us consider that again, statically induced EMF. There we have two coils which are placed near one near to the other, like this. Okay, and these two coils are assumed to be very close to each other, so that the magnetic flux produced by one coil links with the other coil, and we are connecting this coil to a alternating current source, AC source, so that positive and negative will come after each and every half cycles, so that the current will be reversed, and the current is varying also in magnitude like a sine wave. Okay, so let I be the current flowing through this, because this is an electrical circuit and a closed path we have. So when voltage is applied, so a current will flow. So I be the current at an instant of time t. I'm taking I be the current flowing in this manner, and let this be the polarity, plus and minus. Okay, so I is flowing in this coil means this coil will produce a magnetic flux, right? Magnetic lines of force or magnetic flux lines like this. Yes, so many magnetic flux, and also these magnetic lines of force link will link to the nearby uh, coil, that is second coil also. So what happens according to Faraday's laws of electromagnetic induction is this phi is changing with respect to time, phi of t. Why? Because this current I is an alternating current. So I changes means the mmf changes, magnetomotive force changes, mf will be varying, and this mmf is varying means mmf by reluctance is your flux. So reluctance is constant for a particular path for this coil. Let us assume that. So then what happens is mmf is changing, then flux is also changing with respect to time. So that means the flux linkage associated with this coil, that is coil 2 and this is coil 1. So coil 2 changes. So according to Faraday's law, an induced EMF E will be induced here, and E will be equal to N d by dt. Okay, N means this N, the number of turns of the second coil. Okay, and in this is what we have defined our we have named it as statically induced EMF. And at the same time, if you observe, this magnetic flux linkage is also changing. It is also linking with the same coil itself, that is coil 1 itself. So, and also the flux linkage is varying with respect to time. So according to Faraday's law, an EMF is induced in the coil 1 also. That is what you call it as self-induced EMF. Self-induced EMF. That means the that is induced EMF, which is produced due to the flux linkage, due to the change in flux linkage with respect to time associated with the same coil. So we got an induced EMF E here, right? So, and this E, self-induced EMF, and this property is known as self-inductance. Self-inductance. And this self-induced EMF E is found to be directly proportional to the rate of change of current through it, di by dt, and this proportionality constant E is replaced by a proportionality constant L into di by dt, where L is known as the self-inductance of the coil. Now, and the SI unit of the self-inductance, or simply you will say as inductance. Inductance is Henry. Henry. Okay. Now we have the Faraday's law. According to Faraday, we have the magnitude of the self-induced EMF. Induced EMF like this: E will be equal to E n d phi by dt. And also we have the expression for the self-induced EMF as equal to L di by dt. That means this n is the number of turns of the first coil, and d phi by dt is the rate of rate of change of flux associated with the first coil. Okay, n d phi by dt. Now we are equating these two formulas, that is n d phi by dt is equal to L di by dt, and dt cancels, and L is equal to d phi by di, n d phi by di. Or if let us say that phi is the uh, changing flux associated with the same coil, while the change in current through it is I, then L will be equal to n phi by I. That means self-inductance. Another meaning for the self-inductance of a coil is that uh, self-inductance inductance of a coil is flux linkage, that is n phi, associated with the same coil per unit current flow through the same coil current flow through the same coil through the same coil. That means That means if you consider a coil like this, and if you pass a 1 ampere current through this coil, then what happens is a flux. First of all, a magnetomotive force will be developed in this coil, and mmf by reluctance a flux will be developed in this coil, and this flux will be linking the total number of turns of the coil, that is n phi. Flux linkage, that is psi is equal to n phi, and that flux linkage associated with the n number of coils is measured as the inductance L of the coil of this coil, that is for a 1 ampere current. That means if you pass a 1 ampere current, then the self inductance of that coil is equal to the flux linkage, the total flux linkage associated with this coil. Okay, that is L will be equal to the flux linkage per unit current, I. Flux linkage divided by I. This phi we know that from the knowledge of magnetic circuits we have phi is equal to Ni divided by S, mmf by reluctance, and S reluctance S is equal to L by mu0 mu r A. So I have L is equal to N. Okay, N, and phi is Ni by S. So by S means we have by S means divided by L by mu0 mu r A. So reciprocal of that means mu0 mu A divided by L into I gets cancelled, so you will get L is equal to N square mu0 mu A by L. This is our equation for self-inductance of a coil. L is equal to mu0 mu r N square A by L. This is important equation for problem solving. Okay, then we will solve another example problem so that the concept is more clarified. So the example problem is like this: the current in a coil decreases. The current in a coil decreases from 10 ampere to 10 ampere. That means initially it is carrying 10 ampere, and 10 ampere to 4 ampere. That is final value of the current through that coil is 4 ampere. That is 10 to 4 ampere it is decreasing, and it is happening in a 0.1 second time. If the inductance he has given as inductance of the coil is given as 4 Henry. Then find the EMF induced in the coil. Find the EMF induced in the coil. Induced in the coil. So let me model this question like this. Yes, we have a coil like this, which is having n number of turns. N is the number of turns of the coil, and this we have two time instances t1 and t2. T1 is 0th second, that is starting time 0 second, and we have 0.1 second also. After 0.1 second, that is t1 t2. Then current at 0 second is given as 10 ampere, 10 ampere current, and at it is decreasing, and it is uh, made to be, it is decreased to 4 ampere in the time interval 0.1 second. Okay, and so that means we have the mmf is changing with respect to time, as current I is changing with respect to time, and mmf is changing, but the reluctance S is constant. So mmf by reluctance, that is flux is changing. So flux is changing means n phi, that is flux linkage associated with this coil, is also changing. So according to my Faraday's law of electromagnetic induction, we have an induced EMF that is given by n d phi by dt, and that is will be equal to, we have proved that E is equal to L di by dt, where L is the self-inductance of the coil, right? So E is will be equal to, so the examiner is asking you to find out the induced EMF here. So L is given as 4 Henry, so 4 into di by dt, di by dt, that's equal to 4 into di by dt means delta I by delta t, and this E will be equal to 4 into delta I means change in current through the coil, that is equal to final value minus initial value, that is final value minus initial value means final value is 4 ampere, initial value is 10, so 4 minus 10 divided by this, yes, final value minus initial value of the corresponding time, it is 0.1 minus 0. That means E will be equal to 4 into minus 6 divided by point, that is equal to 4 into, so 60 minus 60, that's equal to 240 minus 240. Actually, the examiner asked you to find out the magnitude of the induced EMF, so you have to take the modulus value, so it is equal to 240. This is the answer. Yes. Another important point that I have missed is that the saying this Faraday's law of electromagnetic induction, we have the magnitude n d phi by dt, but the direction here, as in the case of Faraday's law, E is equal to minus n d phi by dt, right? That is given by Lenz's law, and the same Lenz's law is also applicable here also. So E will be equal to L di by dt, and applying the Lenz's law, that means minus L di by dt. Okay, so that means here we have the polarity of the induced EMF as E is equal to minus 240, that is equal to 240 plus 240 volt. That means here we have the assumed direction of the polarity as plus minus. Why? Because the current direction of the current flow is from left to right. That means current always flows from higher potential to lower potential. And also we got the induced EMF direction or the polarity as positive. That means our assumed direction is correct and the polarity is like this, plus minus. So that is the meaning. Now we will move on to the next topic, that is mutual inductance, and also coupling coefficient of coupling. So these are the two topics. Then mutual inductance, we have mutual inductance. Mutual inductance, as its name indicates, we should have two coils placed nearby. Two coils like this. Coil 1, we have coil 2. This is coil 1 and this is coil. And I am allowing a current I to flow through this coil or inductor coil. Okay, and coil 2 is not carrying any current. Then this, according to our previous discussion, we have the current carrying coil will produce a magnetic flux. So this magnetic flux or magnetic lines of forces like this, okay, like this will link the the number of turns, the turns of many turns of the coil itself, and also that is self linkaging, and also it also this flux also links the turns of this coil to place nearby, like this. Okay, like this it is going to link to the coil 2 also. But so the this linking the linking the flux linkage associated with the coil 2 due to the current flowing in coil 1, that is known as mutual inductance. That is, mutual inductance means it is the measure of this it is the measure of measure of the flux measure of the flux linkage associated with coil 2 due to the flow of current in coil 1 which is placed nearby. That means if n1 is the n1 is the number of turns of the coil 1 and n2 is the total number of turns of the coil 2. Okay, and this of flux produced by the coil 1 is phi. Okay, and flux, this is what I mean by total flux phi total, and let the flux phi 1 be the flux linking. Yes, let the flux phi 1 be the flux linking with the turns of the same coil phi 1, and let phi 2 be the flux associated with the second coil, that is linking with the n2 number of turns. Okay, then the mutual inductance is defined as n2 phi 2, that is This is what is uh, the flux linkage. Flux linkage associated with the coil 2. And this N252 divided by I is what is M. Mutual inductance M. Okay. And this will be a constant. That is if that is due to the current I flowing in coil 1. What is uh, the flux linkage associated with coil 2? That is flux linkage. It is the measure of the flux linkage associated with the coil 2 due to the or per current flowing in coil 1. Yes, that is what I mean by mutual inductance. Yep. Now, in the same manner, here the flux phi of phi 1 we have is phi 1, which is the flux linking with this coil 1. Then the flux linkage, total flux linkage associated with this coil 1 will be N1 phi. And then the self inductance or the inductance of the coil 1 we will get it as L is equal to N1 phi 1 divided by I. And the EMF induced EMF it will be E is equal to L di by dt. Similarly, due to the rate of change of flux linkage with this coil 2, we have the rate of change of flux linkage with this coil 2. Then according to the Faraday's law of electromagnetic induction, the same induced EMF, another induced EMF E2 will be induced in this coil 2, and its magnitude will be given by E2 equal to, or E2, actually E2 is proportional to the rate of change of current flowing in the coil 1, that is di by dt, and the proportionality constant is E2 is equal to mutual inductance M di by dt. Okay, so this is our mutual inductance property of two coils. Okay, and if I have another case, if you consider another case that two coils which are having N1 and N2 number of turns, and these two coils are carrying current. Coil 1 is carrying a current I1 and coil 2 is carrying a current I2 in this manner. And these two coils are placed nearby. Okay, these are situated very close to each other. Let us imagine like that. Then what happens is this coil produces a flux phi total 1, phi total 1, and this produces a phi total 2. Okay, and this phi total 1, part of this phi total 1 is linking with this coil 1 itself, that is phi 1, and this, okay, and a part of this phi total 1, that it be phi 1 dash, is linking with this coil 2. Similarly, a part of this phi total 2, that is phi 2, is linking or is associated with the same coil 2, and a part another, and the remaining part, that is phi 2 dash, is linking with the coil 1. Okay, phi 2 dash of this total phi total 2. Okay, so that means we have self inductance of coil 1, that is L1 we have, and we have the self inductance of coil 2, that is L2. And also we have mutual inductances, two mutual inductance, that is M12 and M21. That means M12 is the mutual inductance of first coil due to the current flowing in coil 2, that is I2. And M21 is the mutual inductance of the second coil 2 due to the flux phi total 1 for the due to the current I1 flowing in the coil. That means M12 will be equal to N1, right, N1 by 2 dash divided by I2, and M21 will be equal to N2 into phi 1 dash, okay, divided by I1. Yes, okay. And what happens is we have because of self inductances L1 and L2, we have E1 and self-induced EMF E1 and E2 we have E1 and E2 we have, and also we have mutual inductances M12 and M21. So due to this M12 and M21, we have a mutually induced EMF E12 and E2. We have mutually induced EMF also. So in this coil we have two induced EMF, that is E1 and E1. And in this coil, if you consider, we have again two induced EMFs, that is E2 and E21. So this is all about mutual induced EMFs and mutual inductance. Now we have the coupling coefficient of coupling. Next important terminology or term in this topic, that is coefficient of coupling or coupling coefficient. This denoted by K. Okay, and it is a measure of how close is the coupling between two coils. Between two coils is done. This coupling means magnetic coupling. Magnetic coupling means the coupling through magnetic flux. That is which we have discussed a little bit earlier. Those are known as coupling, magnetic coupling. That is magnetic flux linkage. That's all. So how? So the coupling coefficient of coupling K is a measure of how close is the coupling. That means it is a measure of whether all of this phi total 1 flux is linking this coil 2, or vice versa. That is, all of this phi total 2 is linking this coil 1, or how much of phi total 1 flux is linking with this coil 2, and in other words, how much part or how much percentage of this phi total 2, that is total flux produced by this coil 2, is linking with this coil 1. So its measure is known coefficient of coupling. Okay, now so it gives an idea of what portion of the flux produced by one coil links with the other coil. That means it gives an idea of what portion or what percentage portion of the flux produced by one coil links with the other links with the other coil which is placed nearby. Okay, so from the equations of self-inductances of the two coils, we can written as we can have the two self-inductances equation like this. That is L1 we have to equal to mu 0 mu r n1 square mu 0 mu a by L2 equal to mu 0 mu n2 square by a. Sorry, mu 0 mu r n2 square a by L. If yes, and I am assuming that this cross-sectional area and core length of each coil, which we have previously discussed, this coil 1 and coil 2 is having core length L, same equal core length, and also cross-sectional area A here, or cross-sectional area here, both are equal, A and A. Okay, if it is different, then A1 and A2, L1 and L2, like that. Okay, then the magnetic flux produced in coil 1 due to current I1 is given by phi1, that's equal to mmf by reluctance. mmf by reluctance, that's equal to n1 I1 divided by L by mu A, that's equal to n1 I1 mu m A by L, where this mu m is the permeability of the medium and it is given as mu 0. Okay, and yes, and we have the flux that links with the coil 2. Okay, the flux that links with the coil 2 is only a part of phi 1. That is, part of phi 1 is linking with the coil 2, right? So I'm taking it as, that means a percentage of flux produced by coil 1, that is phi 1. Okay, percentage of phi 1 is only linking with the coil 2. So I have this phi 1 2, that is the portion or the part of phi 1 linking with the coil 2 equal to some k. K is less than 1. Okay, some fraction k into phi 1. A fraction of phi 1. K phi 1. Okay, and this, and yes, where k is less than or equal to 1 and it is greater than or equal to 0. Then the mutual inductance from coil 1 to coil 2 is given by, from the, then the mutual inductance we have the mutual inductance from coil 1 to coil 2, that is mutual inductance M1 2 is given by the equal to the mutual inductance equal to N2, that is number of turns of the second coil N2 into the portion or the percentage of phi 1 linking with the coil 2, that is phi 1 2 due to the current I1, right. Now if you replace this phi 1 2 with the k phi 1, then you will get k phi 1 N2 by I1, and that will be equal to this k N1 N2 N1 N2 mu A by L, right. Why? Because this this phi 1, okay, phi 1 we have we are replacing this phi 1 with the phi 1 with this formula, like say N1 I1 mu M A by L, this formula. This formula we are substituting in here, okay, so we will get this formula k N1 N2 A by L. Okay, this is M1 M1. Now similarly you will get the mutual inductance, okay, from coil 2 to coil 1, that is represented by M21, and you will get it as that is equal to N21 phi 21 N2 phi 21. Okay, sorry, this is N2. Similarly N1 phi 2, sorry, you will get it as N1 phi 21 divided by I2. Okay, you can compare these two exactly opposite. Okay, and again replace this phi 21 with k phi 2, then we'll get N1 k phi 2 divided by I2, and you replace this phi 2 with this the equation for phi 2, okay, and then we will get M21 equal to, similarly we have k N1 N2 mu A by L again. Okay, so then we are going to multiply this M12 and M21, that means M12 into M21, that's equal to M square we have, because M12 equal to M21, so that will be equal to M square. So this will be equal to M square, and this M square is given as M square equal to K square N1 N2 mu A by L into N2 N1 mu A by L. So that is equal to K square. I'm clubbing this N1 here and N1 here. So K square N1 square, okay, N1 square mu A by L into, again clubbing N2 and N2 here, then N2 square mu A by L. So that will be equal to M, that means M square will be equal to K square, this N1 square, that is equal to L1, this N2 square mu A by L is L, K square L1 L2. So K will be equal to M by root L1 L2, where K we have uh, we have defined K as the K is the portion or the percent percentage of percentage of uh, flux, total flux phi 1 linking with coil 2. Okay, so the coefficient of coupling, so and this K is known as coefficient of coupling. K is defined as the ratio of the mutual inductance M to the square root of, that means arithmetic mean. Square root means mean. Arithmetic mean. Okay, arithmetic mean of the product of inductances of coil 1, that is L1 and L2. Okay, that means M by root L1 L2. Actually, this sorry, not arithmetic mean. Actually, this is geometric mean. Geometric mean. Arithmetic mean means you have L1 plus L2 by 2 is the arithmetic mean. Geometric mean means you multiply L1 and L2 and you take the square root of this. That is geometric mean. Geometric mean. So K is equal to M by root L1 L2. Okay. And yes, and if the entire flux produced in one coil links with the other, the value of K will be 1. That is K is equal to unity 1. That means coefficient of coupling is 1. That means the uh, the entire flux produced in one coil links with the other. No flux is wasted or no flux is leakage. Okay, and such coils are said to be tightly coupled or closely coupled. Tightly coupled coils or closely coupled coils. So in our examination, if the examiner asked given tightly coupled coils or closely coupled coils, then you take coefficient of coupling K is equal to 1. Okay, and the value of K is 0 means K equal to 0 means no portion no percentage of the total flux is linking with the which is produced by coil 1 is linking to the second coil. That means these are magnetically isolated. That means I have a coil here and a current I is flowing, flux phi total is produced. Then we have another coil somewhere in the infinity. Okay, so that the flux phi total produced this coil 1 is no way linking the coil 2. So in that way then we will get K equal to 0. Okay, then we will call it as magnetically isolated. Okay, then yes, that's all about this session. So thank you.